In the last two lectures, we have learned a lot about chemical reaction, how to balance chemical equations, and what redox reactions are. But how do you know if your chemicals will start to react by themselves at all? In other words, how do you know if your reaction produces energy or whether you need to add energy to the system before the reaction can occur? The law of conservation of energy tells us that the total energy of an isolated system remains constant. Look at the example on the right-hand side of the slide. Methane, CH4, is a highly flammable gas. This reaction equation shows us that the burning of methane with oxygen produces CO2 and water. Of course, we know that if we burn methane, the reaction just continues by itself. And next to the production of carbon dioxide and water, a lot of heat, so energy is released. We call these types of reactions where the energy is released exothermic reactions. In this case, you see in the graph that the energy of the reactants is larger than that of the products, about 890 kilojoules larger. So, when we burn methane, about 890 kilojoules of energy is released. The minus sign before the 890 tells us that the energy is released. On the other hand, if the difference in energy between the products and the reactants is positive, the reaction is called endothermic. This means that we would need to add energy to the reaction before it can occur. Now, how do we know if a reaction produces energy or if it requires energy? For this, we need to know the reaction energy, the difference in energy between the reactants and the products. We can calculate this using the heat of formation of each of the different compounds. How much energy does it cost if 1 mole of that compound is formed? Fortunately, these energies are known for many different compounds, and they have been recorded in tables, such as the one on this slide. Let's look at the example of burning methane and calculate together whether it's true that 890 kilojoules is released when methane is burned in the presence of oxygen. The change in energy is calculated by subtracting the energy of the reactants from the energy of the products. So, if we write this as a formula, the energy of the products is the energy, or heat of formation, of carbon dioxide plus 2 times the heat of formation of water. Why 2? Well, because we can see in the reaction equation that we form 2 molecules of water for each carbon dioxide molecule we form. From this, we subtract the heat of formation from methane and twice the heat of formation of oxygen. Entering the values for the different compounds as we find them in the table gives us that the total energy that is released per mole of methane that combusts is indeed 890 kilojoules. We can also do this calculation for an endothermic reaction, such as the decomposition of calcium carbonate to calcium oxide and carbon dioxide. As you can see, this reaction needs to have energy added to it, for example through heating, before it can occur. So far, we have been writing reaction equations with just one forward arrow, meaning that the only thing that's happening is that the reactants react to form the products. We call this the forward reaction. However, it is also possible for the reverse reaction to occur at the same time, where the products react back to form the reactants. And we call these types of reactions equilibrium reactions, where the forward and reverse reactions occur at the same time. And we use this double-headed arrow to show this in the chemical equation. To better understand equilibrium reactions, let's take a look at the reversible reaction of hydrogen and iodine to form hydrogen iodide gas. We start this chemical reaction with only the reactants present and none of the products, as you can see in this graph. As time progresses, more of the reactants are converted to products, which means 2 things. 1, the forward reaction rate, the green line, decreases, as there are fewer reactants left to react. And 2, the reverse reaction, the red line, starts to increase as soon as some of the products have formed. And when this reaction has been going on for a long time, it reaches what we call the equilibrium state. In a chemical equilibrium, the number of reactants and products remains unchanged. This means that at any time, the number of reactants that react to form the products equals the number of products that react back to form the reactants. And what's pretty cool is that the equilibrium state doesn't depend on how equilibrium is achieved. Look at our example with hydrogen iodine and hydrogen iodide. If we start the reaction with only the reactants, hydrogen and iodine present, we get the exact same concentrations of the three molecules in this reaction at equilibrium as when we would have started the reaction with only the product, hydrogen iodide present. Thank you for exploring the world of reaction mechanisms with me today.